In this video, we'll talk about k-means clustering. By the end of this video, you should be able to describe the steps in k-means algorithm, explain what the k stands for in k-means, and define what a cluster centroid is. Recall that cluster analysis divides samples in a dataset into groups or clusters. The idea is to group similar items in the same cluster where similar is defined by some metric that measures similarity between data samples. So, the goal of cluster analysis is to divide data samples such that samples within a cluster are as close together as possible and samples from different clusters are as far apart as possible. K-means is a classical algorithm used for cluster analysis. The algorithm is very simple. The first step is to select k initial centroids. A centroid is simply the center of a cluster as you see in the diagram here. Next, assign each sample in the dataset to the closest centroid. This means you calculate the distance between the sample and each cluster center and assign the sample to the cluster with the closest centroid. Then you calculate the mean or average of each cluster to determine a new centroid. Those two steps are then repeated until some stopping criterion is reached. Here is an illustration of how k-means works. A in the diagram shows the original dataset with some samples. In B, initial centroids are randomly selected. C shows the first iteration. Here, samples are assigned to the closest centroid. In D, the centroids are recalculated. E shows the second iteration. Samples are assigned to the closest centroid. Note that some samples changed cluster assignments during this step. In F, the centroids are recalculated again. Cluster assignments and centroid recalculation are repeated until some stopping criterion is reached, and you get your final clusters as shown in F. How are the initial centroids selected? The issue is that the final cluster results are sensitive to initial centroids. This means that if cluster results with one set of initial centroids can be different from results with another set of initial centroids. There are many approaches to selecting the initial centroids for k-means, varying in levels of sophistication. The easiest and most widely used approach is to apply k-means several times with different initial centroids, randomly chosen, to cluster your dataset and then select the centroids that give you the best clustering results. To evaluate the cluster results, an error measure known as the within cluster sum of squared error can be used. The error associated with a sample within a cluster is the distance between the sample and the cluster centroid. The squared error for the sample then is the square of that distance. We sum up all the squared errors for all samples for a cluster to get the squared error for that cluster. We then do the same thing for all clusters to get the final calculation for the within cluster sum of squared error for all clusters in the results of a cluster analysis run. Given two clustering results, the one with the smaller WSSE provides the better solution numerically. However, as we've discussed before, there is no ground truth to mathematically determine which set of clusters is more correct than the other. In addition, note that increasing the number of clusters, that is the value for k, always reduces the WSSE. So, WSSE should be used with caution. It only makes sense to use WSSE to compare two sets of clusters with the same value for k and generated from the same dataset. Also, the set of clusters with the smallest WSSE may not always be the best solution for the application at hand. Again, Interpretation and domain knowledge about what the clusters should represent and how they will be used are crucial in determining which clustering results are best. Note that there are several other metrics that are used to evaluate cluster results. Choosing the optimal value for k is always a big question in using k-means. There are several methods to determine the value for k, and we will discuss a few here. Visualization techniques can be used to examine the dataset to see if there are natural groupings of the samples. Scatter plots and the use of dimensionality reduction are useful here to visualize the data. A good value for k is application dependent. So domain knowledge of the application can drive the selection for the value of k. For example, if you want to cluster the types of products customers are purchasing, a natural choice for k might be the number of broad product categories that you offer. Or k might be selected to represent the geographical locations of respondents to a survey, in which case a good value for k would be the number of regions you're interested in analyzing. There are also data-driven methods for determining the value of k. These methods calculate some metric for different values of k to determine the best selection for k. One such method is the ELBOW method. The ELBOW method for determining the value of k is shown on this plot. As we saw in the previous slide, WSSE, or within cluster sum of squared error, measures how much data samples deviate from their respective centroids in a set of clustering results. If we plot WSSE for different values for k, we can see how this error measure changes as the value of k changes, as seen in the plot. The bend in this error curve indicates a drop in gain by adding more clusters. So this elbow in the curve provides a suggestion for a good value of k. Note that the elbow cannot always be unambiguously determined, especially for complex data. And in many cases, the error curve will not have a clear suggestion for one value, but multiple values. This can be used as a guideline for the range of values to try for k. We've discussed choosing the initial centroids and looked at ways to select a value for k, the number of clusters. Let's now look at when to stop. So, how do you know when to stop iterating when using k-means? One obvious stopping criterion is when there are no changes to the centroids. This means that no samples will change cluster assignments, and recalculating the centroids will not result in any changes. So additional iterations will not bring any more changes to the cluster results. It's time to stop. The stopping criterion can be relaxed to the second stopping criterion listed here, which is when the number of samples changed in clusters is below a certain threshold, say 1%, for example. At this point, the clusters are changing only by a few samples, resulting in only minimal changes to the final clustering results. So the algorithm can be stopped here as well. At the end of k-means, we have selected a set of clusters, each with a centroid. Each centroid is the mean of the samples assigned to that cluster. You can think of the centroid as the representative sample for that cluster. So, to interpret the cluster analysis results, we can examine the cluster centroids. Comparing the values of the variables between the centroids will reveal how different or alike clusters are and provide insights into what each cluster represents. For example, if the value for age is different for different customer clusters, this indicates that the clusters are encoding different customer segments by age, among other variables. In summary, K-means is a classic algorithm for performing cluster analysis. It is an algorithm that is simple to understand and implement and is also efficient. The value of K, the number of clusters, must be specified. And final clusters are sensitive to initial centroids.